Hey everyone, this is Professor Norm Jones at BYU again, and in this next exercise we are going to build another simple rectangular mod flow model, and for our use case we are going to look at an agricultural application. It's common in some areas where you have farms and a high water table to dig agricultural drains surrounding the agricultural land to lower the water table. And this can be done through, sometimes they do it through buried perforated pipes, sometimes it's just a big trench. This diagram at the top kind of shows the concept here. This is a cross section through a site, and down at the bottom we have a plan view of this site. So this would be some land that is being cultivated, and if you have a high water table, sometimes you can accumulate salts and alkali, and so the idea is if you dug a trench on either side here, that would then act as a drain, and so you have recharge in the form of rainfall and or irrigation. And this black line at the top would represent the high water table you'd have under normal conditions. And once you dig these trenches, it draws the water table down. I've got it arching up pretty high here, but the concept is it pulls it down and the water drains away to either side. And so that's what we're going to simulate with this model. We're going to have a top elevation of 3,832 feet, bottom elevation of 3,600 feet, hydraulic conductivity of 4 feet per day, recharge 2 feet per year, which corresponds to 0.0055 feet per day. So I've already done the calculations here for you. And then on our boundary conditions, we are going to have we're going to use a specified head boundary condition on the left of 3,820 feet, and on the right, we're just to make things interesting, we're going to have the drains be at slightly different elevation. So this one will be dug to a depth of 3,824. So the assumption here is that each of these drains has a slight slope to it, and water trickles in from the groundwater into the drain and is drained away. So the bottom of the drain here is this fixed elevation. Now, I mean, technically, if the water table dropped below the elevation of the drains, it would have no impact. But we're simulating steady state conditions, average long-term conditions. These are the only sources of, or only places where water can leave the aquifer, and we have recharge coming in. So we're confident that water is going to be draining toward the drain. So we could either represent them using a specified head boundary condition or a drain boundary condition, and it would basically work the same way. In fact, in our next exercise, after this one, we're going to play with some different features associated with those drains to see how it impacts the solution. But for this case, we are going to just use a simple specified head boundary conditions on both of those two sides. And we are going to have recharge coming in. So our flow budget will be recharge coming in, water going out of the drains, and that should be everything we need. So let's jump back over to GMS, and let's start by building our grid. Let me revisit these grid dimensions here. So it's 3,000 feet long in the vertical direction, or in the y direction I should say, and then 2,000 feet in the x direction. And again, we're going to use a single layer for this. Later on in another exercise we'll convert this to a multi-layer model, but for now we'll use a single layer. 60 cells in y, 40 cells in z, and then one layer, or excuse me, 40 cells in x and one layer in z. Okay, so with remembering those numbers, let's go in and we'll say switch to the 3D grid module and do create grid. And we'll say, again, we're using a local coordinate system, so no base map. So we just leave the origin at 0. And then in the X direction, we have 2,000 feet and 40 cells. In the Y direction, we have 3,000 feet and 60 cells. And in the Z direction, let's change the origin here to 3,600 feet, and the length will make it 232. So again, let me explain why that is. So we have the bottom elevation 3,600 and the top 3,832. So if we set the bottom, the origin in Z to 3,600 and the thickness in Z to 232, then we'll get the correct top and bottom elevations. And so here we go. Click OK, and there we have our grid. And of course, the next thing we do is we do File, Save As, and let's call this Ag Drains 1. So we're going to do a second and third version of this later in our series. All right, so let's then, the next step, as you may recall, is to initialize ModFlow. And we'll say, well, we're going to need a recharge package. So we'll turn that on. Everything else will just be turned on automatically as we need it. Again, checking our top and bottom elevations, 3,832 and 3,600. That seems correct. And our I-bound array should be initialized to ones. Whoops, wrong button. And units, we're using, once again, feet and days for our units. So that should be everything we need there. Let's put in our hydraulic conductivity next. The LPF package is turned on. We're just going to double click on this HK array over here, which gives us direct access to our hydraulic conductivity array. And we'll say we want to do 4 feet per day. We'll put that in, and then let's just double click immediately on our recharge array. And we'll do constant to array, and that is 0.0055. That's quite a bit. That's how many feet per day. It's 2 feet per year is the recharge, and this would be mostly from irrigation, I would imagine. That in terms of recharge, that's a really big recharge rate. But if you're doing flood irrigation, that's not unheard of. All right. So let's save our changes. Moving along very quickly here. Next, we're going to put in our boundary conditions. We are going to do a constant head boundary condition on the left. So using the select cells tool, I drug a box around that vertical column, or that column of cells on the left. And then I'm going to right click and select properties. And remember from our last exercise, we learned that to set a specified head boundary condition, you change the I-bound value to specified head, which changes the underlying integer value to -1. And then in the starting heads array, you enter your desired head value. So this should be 3820. Okay. And then again, once we're done, it shows up as specified head cells. And then I'm going to use the select column tool for this. And I'm going to double click on that column on the right. Do specified head, and this one is 3824. All right, so we have we've done our hydraulic conductivity, we've done our top bottom elevations. We've entered the hydraulic conductivity, the recharge, specified head on the left, specified head on the right. We should be ready to go. So let's give this a shot. Let's do our check simulation option. And I don't see any errors or problems there. And so now let's save that and run ModFlow. Converges very quickly. And what do we have? So this is our solution. We have the maximum head value is 3825.4, somewhere here in the middle. Again, as you move the cursor across the grid, you'll see down here in this little F section at the bottom of the screen that will show you the current head value out to a ridiculous number of significant figures. And so we have mounding here in the middle, and then it over to the left it goes down to 3820, and over to the right it goes to 3824. So that appears to be okay. Now let's go into side view, and let's see here. Let me get the right one. Yeah, this is the one I want. And you look at that, and you say, well, there's not much variation there. Can't really see much change. They're very small. 4 feet per day is a pretty high value of hydraulic conductivity. So you get a pretty flat water table. So I kicked that up to the Z magnification. So the vertical magnification is set to a value of 5 now. So you can start to see a little bit of variation there. Again, it mounds right here in the middle. It does, or right here, I should say. The mounding does not occur at the true center because these the specified head on the right is higher than the specified head on the left. Otherwise, it would be symmetric about the center of the grid. So that's all there is to it. Let's try something just for fun. Let's go back to plan view. I'm going to increase that recharge rate just a little bit. Instead of 0.0055, let's change it to 0.008. Just increase it by 50% or so. And see what that does to our solution. So here we are. 3826. Let's go into our side view. Well, so now we get a little bit higher mounding. Not a huge difference, but it is a little higher in the middle. Another thing we can do is decrease our hydraulic conductivity just for fun. So let's go down from 4 to 2. That's a pretty big change. It'll probably cause some serious mounding in the middle of our model. So yeah, there we go. So now it's up to 3830. Not as much as you'd think. When you have two specified head boundary conditions as close as these are, you're not going to have a significant change here in the middle. Those are really strong boundary conditions. But it is higher. I think it was 3824 before in the middle. Now it's 3830. So it definitely mounds higher than it did before. And it's going to look about the same in the middle. The shape's going to be the same. We're just changing the amplitude of that. So anyway, real simple exercise. Pretty much all there is to it. And we're going to come back to this in a couple of future use cases to make some modifications and see what happens.